Welcome to the group exhibit Hydrogen Fuel Cells and Batteries at the Hannover Fair 2017. We are here at the Technical Forum, and this is the last presentation regarding energy storage. And I'm happy to have here Dr. Mihails Kusnezoff. He will talk about solid oxide cell co-electrolysis operation, new option for chemicals production. I will hand over to you right now. I hope you have something to drink, a coffee, some water. Otherwise, help yourself at the bar. Stage is yours. Thank you very much.
Thank you very much for your kind introduction. And I simply want to show you our last results we have achieved on solid oxide cells for steam electrolysis and co-electrolysis operation and compare them to SOFC operation. So I will do a short introduction about our institute and then come to the core of the topic. And will guide you through SOFC, SOAC, and co-electrolysis operation. Yes, we are the largest ceramic institute in Europe, and energy is a big field for application for ceramics, and especially solid oxide fuel cell in the past was a topic where we have concentrated our efforts because it has ceramic electrolyte made of zirconia, which is conducting for oxygen ions, and you can build a very high efficient units based on solid oxide cells. Here you see the reference projects we have done in field of SOFC. So we were concentrated on off-grid power generation or micro CHPs with different companies. And now we are seeing a new potentials for this technology, especially in field of electrolysis. If we consider the solid oxide cell, then we can operate it in two modes. One is solid oxide fuel cell mode or fuel cell mode. In this mode, you generate electricity and heat. So in this mode, the cell can operate self-sustaining because it generates heat for sustaining the operating temperature. In electrolysis mode, it is opposite. So you don't generate any heat, you consume heat. Here, you should provide electricity and normally heat for operation. But if heat is generated by internal resistance of the cell, then you can achieve endothermal operation and very high efficiencies for conversion. If we look to thermodynamics, then we will see that even for high temperatures, the electrolysis is more advantageous than for low temperatures because you need less energy for splitting of steam. It is simple thermodynamics, so you have lower OCV, so you should apply lower voltage to split water molecule in hydrogen and oxygen. Based on this, we can integrate SOAC technology as producer of energy with high efficiency, utilizing the common fuels, as well as generator of the chemical energy, which is saved in the fuel, and provide new options for our grid in the future. And this is a reason why we think that electrolysis or solid oxide electrolysis is a good option which should be explored. Now we simply start with the state of the art. So we are working on planar stacks, and we are following CFY technology which we have developed together with company Plansee. And this stack consists of bipolar plate, which is a chromium iron alloy, ceilings, and the cell itself. And the cell is a key for conversion. So you can make different electrodes you can optimize them, you can lower the resistance and achieve higher efficiencies. Of course, you cannot realize resistance zero, but nevertheless, you can realize very small resistances. And the state of the art of SOFC technology is very good. So we can now realize cells with very small resistances, even electrolyte supported, utilizing the high conductivity electrolytes. And this with very high accuracy. So we can reproduce the cells in terms of the electrochemical performance. We can also add properties such as redox stability or sulfur tolerance, depending on materials we are utilizing in the cell. Now, what is about long-term stability? In SOFC operation, normally we have solved the problem of the long-term stability. Often we simply activate the air electrode during operation, and only processes which are responsible for degradation happening on the fuel side. Here you see the graphs of testing of our G3 cell for SOFC operation, and you see that even scattering of the data is more than the degradation we can measure. So for this reason, we are running the cells 4 times, more than 4,000 hours, to determine the degradation rate. If we put the same cell in the operation mode of steam electrolysis, then we see that we have nearly 2 symmetrical characteristics. So we operate the cell in fuel cell mode, the draw electricity, or we apply power and generate hydrogen, and there is no change in the OCV and no big change in the characteristics. But if we analyze it using impedance spectroscopy, then we see that if we move from SOFC operation to electrolysis operation, steam electrolysis or co-electrolysis, then we see some increase of impedance, and we have justified that it is connected with ohmic losses and with some diffusion losses in the fuel electrode. Then we have observed very interesting phenomena. Depending on the temperature we operate the cell, we can see some short-term degradation or short-term effects for stabilizing the operating voltage. For example, at 800 degrees, we observe such saturation of the voltage, which takes place in the first, I would say, 100, 120, 200 hours. And if we increase the operating temperature to 830 degrees C, then we don't have such effects. These effects are also reversible, so if we put the cell in the fuel cell mode, then we don't observe it. So we wanted to investigate how we can diminish this effect and tried to change the porosity of the fuel electrode, and at the same time trying to improve adhesion of the air electrode, because it is known that on our electrolysis operation, air electrode can be delaminated from the electrolyte, especially at higher current densities. So then we have moved from G3 to generation 5 cell, and you see here the basic characteristics of the cell. Made by impedance spectroscopy. So in G5 cell, we have applied additional interlayer, and then we have increased the thickness of the fuel electrode and also homogenized the porosity in the fuel electrode. Now we are coming simply to stack performance. So we have tested all these cells also in the stack. And the difference in the stack operation in fuel cell mode and electrolysis mode is not always evident for people who are first time working with this technology. The difference is that in the fuel cell mode, normally you generate electricity at the point where current flows. It means you can create hot spots. And it means also that in fuel cell operation mode, you should take care about temperature homogenization. In the electrolysis mode, it is opposite. Where you draw the current, then at this point you consume the heat. It means also at this point you don't have a big hotspot, so the consumed heat diminishes the effect of high current in terms of overheating. So in electrolysis mode we have very homogeneous temperature distribution, which helps us to operate the cells. If we look on the performance, then in SOFC mode we can operate our cells up to 30 watt per cell and achieve current densities of 400 milliamps per square centimeters, and delivering from 30 cell stack the power range from 850 to something like 1.2 kilowatt. In electrolysis operation, we apply power. So we can also generate a map, performance map, but in this case we need some heat source to operate the stack, and this is furnace which we have used. And then we have simply looked on thermoneutral operating point. It means we have achieved the same temperature of inlet air as of outlet air, adjusting the current. And here you see the power we need for thermal neutral operation of such a cell at different temperatures. And you see also increasing the temperature, we reduce the power consumption. We also observe in the stack operation the same effects we have seen on the cell level. So especially at 800 degrees C, we see some effects which are explained as a stabilization, which are also reversible. And if we increase the operating temperature, then they are diminishing. We have also tried to switch between SOAC and SOFC mode, and we also have seen that in this case, even by operation at 800 degrees C, 12 hours in one mode and 12 hours in other mode, we don't see a big degradation, because normally after SOAC operation, the change we induce at low temperatures are reversible if we operate the cell in the SOFC mode. So our hypothesis is that these changes are connected with the electrode structure, and we have changed the electrode structure in this G5 cell and then operated this cell in steam electrolysis or co-electrolysis mode. So here now we switch steam electrolysis to co-electrolysis and simply compare whether we need more power for co-electrolysis operation. And what we have seen, it is not so. So we need only 2% more power. And this provides us an option to get the same efficiency for co-electrolysis as for steam electrolysis. And I will show in the future what opportunities it can give. Here again, degradation. We have also investigated whether degradation in co-electrolysis mode is different from steam electrolysis with the same cell, and we have seen no difference. And it is a very good message for everybody who wants to make a solid oxide cells. We already put the generation 5 cell And we have seen that we have less degradation with this modified electrode structure, and also at 800 degrees, we don't observe anymore this relaxation phenomena as we have observed with non-optimized fuel electrode structure. Now about future. So we think that this option for providing direct conversion of mixture of steam and CO2 is very interesting for combination with Fischer-Tropsch synthesis. Because in this case, we have only one reactor which converts both components and also adjusts the stoichiometry. And in this case, we can use temperature as an equilibration factor to adjust stoichiometry between hydrogen and CO, which is needed for chemical synthesis. If we look on energy consumption, if we want to produce different ratio of steam to CO, then we see that the difference is also not very big. And if we compare it to PEM and alkaline electrolysis, you see a huge difference in the energy demand. It means if we can realize big electrolyzers using SOC, then we have a huge energy advantage. And this will beat all investment costs in the future, believe me. If we consider 20 years of operation of such unit, then the investment costs will be reinvested by electricity cost. This is, I think, our outlook. So to couple this process with Fischer-Tropsch, we are working on this. I want only to show you the short summary. We think that solid oxide cell is a good technology for SOFC and for electrolysis operation. We think that we have done the first steps in this direction, but there are many steps which should be done, especially in terms of long-term stability. And I want to thank you for your attention. And in the hall 2, we have presentation on Fischer-Tropsch synthesis on Thursday from Stefan Megel. And if you are still here, then you can go there and hear about the details of conversion of this synthetic gas to alcohols and other chemicals. Thank you for your attention.
Thank you very much, Dr. Mihails Kusnezoff. Are there questions right now? If not, I would like to continue because we're a little bit behind the time. If you have later on questions, the booth number will be E51. Just pass by, have a look, have a chat. Yes, thank you one more time.
Thank you.
The next presentation will continue in a few minutes. It will be with John Eriksson, CEO of Hystorsis, and it will be regarding thermal hydrogen compressors. Thank you.